All right, so in this lecture I would like to come back to, let's say, a broader overview of what computational science is. In particular, I would like to talk about time-dependent problems. So in the past we've talked about the Laplace equation, and we've talked about the mixed form of the Laplace equation, and I've shown you a few programs that deal with problems that have multiple solution variables, for example step 20 and step 22 for the Stokes equation. All of these were time independent, and what I would like to talk about in this lecture and in the next few is time-dependent problems. So the first task that I would like to talk about is essentially a taxonomy of time-dependent problems. There is, let's say, three broad classes of time-dependent problems that most problems, let's say, don't necessarily fit into each one of these classes, but they share the character of the prototypical elements of these classes. And so what I would like to do is give you a little bit of an overview of this and give you an overview of the two primary methods of discretizing the time dependence of these problems. That is called the method of lines and the Rother method. So here's a broad overview of everything you need to know about time-dependent problems. Not quite, of course, but let's say it shows you the prototypical classes. Namely, there are three equations that we always consider as the prototypes of these classes. The first one is the heat equation, and it is the prototype of a class of equations that we call parabolic equations. So the heat equation is an equation where you have a solution variable u of x and t, of course. And the heat equation says that the time derivative of this solution variable equals the Laplacian of u plus some right-hand side. It's called the heat equation because it describes how heat dissipates in a body. So we immediately know, for example, that for the heat equation, what we have to expect from the solution is that you start out with something, for example, that is that has discontinuities or that has a peak. Very quickly, it will just dissipate. It will diffuse, right? So we expect the heat equation, because we know what the underlying physical model is, we expect the heat equation to have smoothing properties. And indeed, we can show that mathematically this is true. The second equation is the prototype for what we call second-order hyperbolic equations. And the prototype for this is the wave equation. The wave equation looks a lot like the heat equation, except that it has second time derivatives here. And as a consequence, where for the heat equation I had to pose initial conditions, because here I have two time derivatives, I have to pose initial conditions not just for u, but also for the time derivative of u at the initial time, so at t equals 0. The wave equation has an entirely different kind of behavior than the heat equation. So for the wave equation, it takes its name because it describes situations where you excite a wave and it travels along a medium, for example, along a string or a telephone line, or maybe if you throw a rock into a lake, how the waves propagate outward. So for the wave equation, we do not have this sort of smoothing properties. Maybe the wave becomes smaller over time, gets attenuated, but it doesn't change its shape. So if you have a spike at the beginning or a discontinuity, the wave equation preserves this. And that's a fundamentally different character than the heat equation, and something that we will have to take into account when we discretize things. The third equation is what we call the transport equation, and it is the prototype for a general class of problems that we call first-order hyperbolic equations. Sometimes we refer to them as conservation laws. And so the transport equation looks like this. It has a first time derivative of this solution variable, but then it doesn't have second spatial derivatives, but only first spatial derivatives. So there is a gradient of u, and we take the dot product with a prescribed vector v that we oftentimes consider as, let's say, a vector field, let's say a flow field or a wind field. And again, you have to impose initial conditions for this. So what this equation describes is essentially the transport of material in a prescribed wind field. So think, for example, of pollution transport in the atmosphere, or the transport along of the temperature or of the salinity in the ocean. These sort of things are described by first-order hyperbolic equations like the transport equation. So the transport equation, again, is an equation that does not have any smoothing properties. If you have a sharp spike, it's going to be transported along as a sharp spike without diffusing. So if you have this equation, again, there is no smoothing. The first-order hyperbolic equations in general are often considered not in this particular form. So this is a linear equation here, which is relatively benign. Oftentimes we consider first-order hyperbolic equations, let's say conservation laws, as nonlinear equations. So there would be a term here that only depends on u and the gradient of u, but not second derivatives of u. And in that case, these conservation laws, these first-order conservation laws, have rather nasty properties. Namely, you might start with a smooth solution, let's say a sine function, and after a while you get something that has a shock, a discontinuity. So transport equations, or let's say the transport equation itself, is not all that difficult, but first-order hyperbolic conservation laws oftentimes have very difficult properties that we need to reflect again in the discretization. So in a, let's say, levels of difficulty, the heat equation certainly is the simplest one because it has smoothing properties. The wave equation does not have smoothing properties, but it doesn't make things worse either. Whereas if you go to nonlinear transport equations, they can make the solution worse. You can start with a smooth solution and you can end up with something that has a shock. So these are the three broad classes that, let's say, we have of time-dependent problems. And like I said, in reality, of course, let's say if you're given an equation, it does not neatly fit into this scheme. So there is a mathematical definition of what a parabolic equation is, and the heat equation is one representative of this. Typically, when you have an equation, it does not necessarily satisfy the let's say, requirements for being a parabolic equation. But it might satisfy, let's say, the moral, it might morally fit into this category by virtue of having the properties. So the solution has the properties of solutions of parabolic equations, for example. And I would like to give you a few examples of equations that are similar to these templates, just to give you an idea of how you would characterize these time-dependent problems. So the first example that I would like to show you is the Stokes equation. Now the Stokes equation looks a little bit like the heat equation. It has a first time derivative of the solution u. So for the Stokes equation describes slow viscous flow. And in this case, u would be a vector-valued variable that describes the velocity vector at every given point. So the first equation would be that the time derivative of u minus the Laplacian of u equals the right-hand side plus or minus the gradient of a pressure variable, p. So the flow is driven not just by the forces on the right-hand side, but also by pressure gradients. And I have a second equation that says that the divergence of u equals 0. So these two equations together are sufficient to determine u and p. And it's not exactly a parabolic equation because there is no time derivative on the pressure, right? The only time derivative that appears here is of u. There is no time derivative on the pressure, and as a consequence, there is also no initial values for the pressure. But let's say morally or conceptually, the equation is parabolic, because if you start out with something that has spikes, over time you end up with a smooth solution. You can think of this as, let's say you have a volume of fluid, and if you stir very localized at one particular place, over time the stirring will yield a large eddy that will eventually dissipate. Okay, so that has certainly the character of a parabolic equation, even though it does not immediately look like a parabolic equation, or it doesn't satisfy the formal requirements of a parabolic equation. Conceptually, you can think of the Stokes equation as a heat equation on the subspace of functions that are divergence-free. And in that case, it becomes clear why it is a parabolic equation. But let's say the way we write it here, it's not obvious. The second example I would like to show you is the Navier-Stokes equations that describe, again, flow by a viscous fluid. But not just slow flow, it can be fast flow in this case as well. And so in that case, if you have fast flow, you also have to take into account the effects of inertia. That fluid that moves doesn't immediately want to stop. It just wants to keep going in the same direction. And mathematically speaking, this leads to the addition of this one term here, u dot gradient u. So you could say, well, if the Stokes equation was parabolic, then certainly this one must be parabolic too, right? It's just a lower order term that I add. What could possibly go wrong? But there's a little bit of a twist here. So there's a parameter here that in the Stokes case we can typically set to 1. That here we can't. We need to actually look at its size. This is called the viscosity nu. And what's happening is that if this nu is small, if this nu is large, that means we have a very viscous fluid. Then if nu is large, then the velocity is small, and the quadratic term here is going to be smaller than the linear terms. And in that case, indeed, the character of the equation is parabolic. But if the viscosity is very small, or the velocity is large, then that means that this term here is going to be smaller than this one, because it is quadratic and the velocity is large. And then you end up with something that has the character of a hyperbolic equation, right? Because it's essentially a transport equation, right? We have a velocity field times the gradient of our solution variable. That's the characteristics of a first-order hyperbolic transport equation. So depending on what the size of these parameters, or in this case of this one parameter nu is, you can either get something that is parabolic or hyperbolic in character. A third equation would be, let's say you have two-phase flow in porous media. So porous media are often described by the mixed Laplace equation that we have looked at previously as a prototype of a vector value problem. So you would have a velocity u that is equals to minus k grad p, or I can write it like this. Okay, so I have the pressure, the velocity is given by the gradient, or is proportional to the pressure gradient. Then I have that the divergence of u equals some source term. So that describes u in p. And then with this velocity, I advect along a saturation variable. So if I have two-phase flow, I just typically describe this as, let's say s equals 1 would be all water, s equals 0 would be all oil. Okay, s equals something between 0 and 1 would be a mixture between oil and water. And this mixture is transported along with the bulk velocity that I describe as u. The first of these two equations is certainly hyperbolic. The other two equations have no time derivatives at all. And so how can we think of this? So one of the ways we like to think of this is that they are instantaneous. They have to hold at every given time. So for every t, these u and p have to satisfy this equation. And what that means is that u and p have no memory. So u and p at any given time does not depend on u and p at a previous time, because there's no time derivative, right? We can think of these as constraints to the equation, as instantaneous constraints. And if this was a differential equation, an ODE, then we would call these sort of systems differential algebraic equations. So a DAE is an ODE with an instantaneous constraint. This is sort of the character of these equations. So I have a hyperbolic equation with an elliptic, with essentially the Laplace equation, with an elliptic instantaneous constraint. Then the fourth example I would like to give you is that a generalization of the transport equation, namely where I have du over dt equals or plus the divergence of some function f of u. Okay, so that is what we call a hyperbolic conservation law. This is in fact what we call the conservative formulation of a hyperbolic conservation law. Depending on what exactly the form of this f is, so if u is a vector valued variable, let's say It could be in gas dynamics, it would be the dim components of the velocity plus the pressure plus the temperature, for example. So you would have dim plus 2 components, and this F would be a matrix that is dim plus 2 times dim plus 2. If I take the divergence, I get again a vector of size dim plus 2. Sorry, that's not true, of course. F would be a matrix that is dim by dim plus 2, and if I take the divergence of this, I get a vector, because the divergence is a vector of size dim, I get a vector of size dim plus 2. So depending on what the exact form of this F is, it might be degenerate. So it might not actually be hyperbolic in the strictest sense, but let's say morally speaking again, this equation is hyperbolic. Sometimes you have that this F does not just depend on u, but also on gradient u. That would make this problem formally parabolic. But typically, the dependence on the gradient of u is small. So it becomes parabolic because I would have the divergence of something that involves the gradient of u, so that would involve second derivatives of u. That's what makes it parabolic. Morally, it is still a hyperbolic equation if the dependence on gradient u is weak. So typically what you have, for example, in hypersonic flow is that you have a very small viscosity, but a very large inertial term. So you have, let's say, not quite that a discontinuity develops in the solution, but that the solution has at least a very sharp gradient. So the solution remains continuous, but it has a sharp gradient, and as a consequence, morally, you will still have to deal with something that behaves like a hyperbolic equation. So the conclusion of this is that when you see an equation that is time-dependent, let's say you talk to somebody in the applied sciences, to a geoscientist, or to somebody from the atmospheric sciences, and they give you an equation, then oftentimes what you will find is that these equations do not satisfy a strict classification. So let's say they don't always you cannot always say just because they have second spatial derivatives they are parabolic. But you have to look at the size of the relative terms. If the second derivatives are large, then yes, it's parabolic. If they're small, then maybe it is still hyperbolic. So more often than not, what you will find is that you cannot strictly classify equations, but that these equations or the solutions have properties that make them similar in character to hyperbolic or parabolic problems. And that depending on what their character is, you have to choose spatial or temporal discretizations that we have to choose for these different classes. So the 3 different classes I introduced, I did this because there are typical techniques that we use for each one of these classes. And when you see an equation and you have identified which category it belongs to by character, then that already identifies what kind of discretization we have to choose. So we typically develop these methods on model problems that like the heat equation, the wave equation, or the transport equation, and then we apply the methods that we have found work for model problems also to problems that are similar. There are 2 different ways, basically, how to approach discretization in space and time. And I would just very briefly like to show them to you. So the first one is called method of lines. And essentially what you do is you first discretize in space, and then you still have the time derivative. So you get a very large system of, potentially very large system of ordinary differential equations that you can use like any other ODE. So you just stick them into an ODE solver. Maybe you have 10,000, 100,000 grid points, so you have an ODE system with 10 or 100,000 solution variables. But essentially you treat this as an ODE. The alternative would be what is called the Rother method. Namely, you first discretize in time, and then what happens is that you get a PDE at every time step. And I personally prefer that approach because it gives you a spatial problem at every time step that you can solve separately from the previous one. So, for example, you could choose different meshes from the previous time step to the current one. And oftentimes when you have features that are transported through the domains, think for example the wave equation, you want to choose the mesh different on each time step from the previous one. because the places where you need mesh refinement have moved from the previous time step. So the Rother method gives you that sort of flexibility. What you will find is that if you keep the mesh fixed, so let's say you only solve on a uniformly refined mesh that doesn't change between time steps, then oftentimes the two approaches actually lead to exactly the same solution. You can show that it doesn't make any difference whether you first discretize in space and then in time, or first in time and then in space. But if you do want to use different meshes, then the Rother method is conceptually more flexible. So to show you the Rother method for a parabolic heat equation, for the prototypical parabolic problem, think, for example, so this is the equation here. The simplest way to discretize this in time is that I say, well, I introduce variables un, which approximates the solution at time tn, and I already have the solution on the previous time step, un minus 1, which would approximate the solution at times tn minus 1. And tn minus 1 I'm going to call delta t. So the simplest approximation is the backward Euler method, which replaces this time derivative by the finite difference gradient in time. So it would be, or the finite difference derivative. So it would be un minus 1 divided by delta t. And then the backward Euler method evaluates this term with the Laplacian at time n, and it evaluates the right-hand side at time tn. Okay, so this gives me a PDE for the solution un at time tn, right? So I already know un minus 1. I can compute un as the solution of this equation, and we can, this is a PDE. I can discretize this PDE at time tn separately from the previous time steps. So the opposite approach, of course, would be the method of lines, which does essentially the following. So in this case, I'm going to leave the time derivative in place, and I'm going to discretize this in space. So I do this with the typical finite element approach. I multiply from the left with a test function phi h. I replace my u by a uh, a discrete solution. Then I write my uh as a linear combination of these shape functions. This should be a phi j here, of course, times uj and the sum over uj. And then what I get is that if I take this expansion and I plug it in here, and I plug it in here, and I integrate this by parts, I get something like this. So a mass matrix times the time derivative of this vector, capital U, that's the vector of coefficients, plus the Laplace matrix times U equals f. And that's just a very large ODE system. So I can give this to any ODE integrator. There are packages for this. You can also do it in MATLAB, for example, and it's going to give you the solution in terms of these expansion coefficients uj as a function of t. So after this brief introduction into, let's say, the taxonomy of equations and the two basic approaches of discretizing them, what I would like to do in the next few lectures is that I come back and I look at each one of these classes in turn. And I'm not going to talk about the spatial discretization, because that works with finite elements just like we've always shown it for all of these equations. So essentially you multiply by test function, you integrate by parts where necessary, and you get a linear system. But what I would like to talk about is, let's say, the kinds of time discretizations that you can use. So I showed this to you for the implicit Euler method, and I would like to discuss this for the heat equation and for the wave equation. I would like to talk about, let's say, the kinds of time discretizations that you can choose for these sort of problems and what that leads to, and let's say what the implications are. So the next lecture will be on discretizing the heat equation, and the lecture after this on the wave equation.